In our last lecture, we discussed the various representative schemes of regions, and there we had considered three different representation schemes. The first one was based on chain code. The second representation was based on polygonal approximation. And the third representation was based on 1D signatures. Now in all these representations, essentially we are representing the boundary of a region, that is to say the external characteristics of a region rather than its internal characteristics in terms of the pixels which comprise that particular region. Now continuing with our discussions on the boundary representations for images, okay, we will describe two other representation schemes, okay, and the fourth one which we are going to discuss now is based on boundary segmentation. Where, as opposed to the polygonal approximation, we need not segment the boundary of a region into elementary linear segments. Rather, we will be segmenting the boundary based on some prominent convexity properties. So, for that matter, what we consider is a representation based on the convex hull properties of boundaries. So let us consider an object, okay, which is having this kind of a shape, this kind of a boundary shape, let us take. All right. Now this region, okay, which we have drawn within this green boundary can be described by a set. Let us call that set as a set S, okay. That means to say set S is a set of all pixels within this region. Now the first definition is concerning the convex hull for this particular region. Now by convex hull we mean to say that it is the convex hull is actually defined as the smallest convex set which contains S entirely, okay. So convex hull is the smallest convex set enclosing S. So the convex hull would look something like this. So the region which I now indicate with the red border is the convex hull for this region which is given by this set S, okay. And the region enclosed within the red, okay, is also a set. It is also a set of pixels, and let us call that set as the set H, okay. Now the set which is formed by subtracting the set S from the set H, okay, that is called as the convex deficiency for this region, okay. So convex deficiency, by convex deficiency we mean to say the set D which is formed as H minus S. Okay. So that means to say, if we consider this region, which is shaded with black, okay, the region shaded with black now indicates the convex deficiency. Okay, whatever I shade like this is nothing but the convex deficiency. Now, by using this definition, one can represent a region in terms of the convex hull properties, something like this. Now, one can partition a region boundary like this. One can start with any arbitrary point. Let us say somewhere here we take our starting point along which we will trace out the contour. Now, while tracing the contour, okay, let us say that we are traveling in the clockwise direction, and while traveling along the contour, okay, whenever we encounter any new convex deficiency component, okay, we mark those particular points. Like this entire region has been separated into a number of convex deficiency components. Say one component is like this, the other component is a small region which is in this zone, then again another convex deficiency over here, then yet another small component over here, yet another convex deficiency, yet another small convex deficiency component over here, then another one, and here maybe a minor convex deficiency region. Okay, so this is how we have represented this particular region. Now, whenever by tracing along the boundary of the region, okay, we encounter a change in the convex deficiency component, okay, we mark those points. Like say for example, here we are encountering a change in the convex deficiency component, so we mark this particular point. So we are in a new convex deficiency beyond this. Okay, once again when we come out of this boundary point, again we are encountering another new convex deficiency, so we mark this point. Okay, we proceed, and somewhere over here we encounter another new convex deficiency, so we mark this point, this point. Like this we can mark all the prominent pixels, okay, where we are encountering a change in the convex deficiency component. And now what happens as a net result is that the entire boundary of the region S, okay, has been separated or rather segmented into a number of components. One is a smaller component like this, again a bigger component, again a smaller component. Like this we have segmented the entire region, okay, segmented the boundary. And now every such segments basically indicates, I mean if we are segmenting it according to the convex hull property which we just now described, in this case every I mean the segmentation of the boundary is being done in such a manner, I mean the segmentation automatically takes care of the points of inflections. Okay, now here you can very clearly see that the points of inflections are automatically considered in the boundary segmentation process. Okay, now I mean in terms of convex hull, actually a number of descriptors also have been used, okay, for the regions, and the commonly used descriptors are, first is in terms of area. That means to say one can simply represent a region by considering the area enclosed within this region. Okay, the area enclosed within this region is, okay, that can be a very simple descriptor. And how do you find out area? Simply by having the number of pixels, by counting the number of pixels which are there within the enclosed region. So that is the area. Then, yet another descriptor which is based on the convex hull property is area of its, in terms of area of its convex deficiency. If you can calculate the area of the convex deficiency, that also can serve as a descriptor. So, descriptors based on convex hull property. Okay. Now, the third descriptor which is used is the number of components in convex deficiency. Number of components, we simply mean the number of disjointed regions in the convex deficiency. Now, very clearly this region and this region and this region, all these regions are disjointed. So, there are 1, 2, 3, 4, 5, 6, 7, 8 such components in the convex deficiency in this particular case. Okay. Then one can also describe, put descriptors based on relative locations of convex deficiency components. Okay. Now, this representation is sometimes chosen, okay, for representing the boundaries of objects in terms of its convex hull properties. Then yet another region representation, that is to say the fifth one in our list, okay, after the boundary segmentation, the fifth representation which we are going to cover is based on the skeleton of a region. Now, a region is represented something like this. Supposing we have a region of this nature. Now, what we do? We take every pixel within this region, okay. There are so many pixels enclosed within this region, and we consider each pixel individually, alright. And for each pixel, we find out that, which is the nearest boundary. Now, if there is only one nearest boundary, okay, then we do not take any special consideration for those points. But there will be some pixels within this region where there will be more than one nearest boundaries. Like say for example, if we consider any pixel which is exactly at the middle of this, okay. Now, this is having a distance d from the boundary, okay, which is shown on the top. Now, this is also having having the same distance d from the bottom boundary, okay. So, this is having more than one nearest boundaries, okay, present, and such points which are having more than one nearest boundaries, they belong to what is known as the medial axis, okay. So, we define the medial axis follows, medial axis as follows. For each point P in R, okay, R means the region, okay, find its closest neighbor. Find its closest neighbor along the border B, okay. Now, if P has more than one such neighbor, then P belongs to what is known as the medial axis. So, if we now make an exhaustive search over this entire region, means if we now search over the entire pixel space within this region, we are going to find out a certain set of points, okay, which we fulfill, which will fulfill this property, that which is equally closest to more than one neighbors on the boundary, okay, and the locus which we will get in this process would look something like this. Isn't it? Or rather, let me indicate this with a different pen so that this is very clear to you. So, whatever I am showing by the red pen, okay, all the pixels along this, okay, correspond to the medial axis, and this entire region, okay, this entire region R which we had, okay, has now been transformed into what? It is transformed into a skeleton. It is just transformed into a red skeleton like this, okay, and this red skeleton corresponds to the medial axis. So, the transformation which we apply in this process is known as the medial axis transformation. In short form written as MAT, all right. Pardon? Yes, why not? Let us consider some object of this nature. Let us say an object of this shape. All right. What will be its medial axis? Should be something like this. Pardon?
No, closest neighbor.
Closest neighbor.
More than one.
Closest neighbor you are considering. So, it will be something like this. Am I correct? Okay, something like this you will get as the medial axis. So, again this red line, okay, which you have seen over here, this is nothing but the skeleton of this entire green region, okay, after application of the medial axis transformation. So, this process is either called as medial axis transformation, or it is also called as skeletonizing algorithm, or it is also called as thinning algorithm. Thinning algorithm is actually very widely used in image processing, because wherever we have any thick objects, okay, and especially thinning algorithm is very often used in character recognition problem, because supposing we have written a character something like this, supposing this is the way we write a character. Okay. Now, this is a thick set of pixels which will consist of this particular character, and if we would like to recognize that which particular character it is, okay, the first step which is usually done is to apply a thinning algorithm such that the character is transformed to something like this. All right, that means to say it is transformed to a skeleton, and there what we do is that progressively we reduce the size of the object, okay, till the time the object doesn't vanish, okay. That means to say we keep on contracting the image, but always we retain the skeleton. Now, of course, from these results, what you see is that we get a very neat picture of the medial axis transformed image, okay. But the process which is involved in this, okay, is not a trivial process, because what is the problem that you will encounter in finding out this medial axis transformation?
Not unique.
It is going to be computationally intensive, very intensive, because you have to consider you have to compute the distance from every pixel, okay, to its nearest neighbors. That means to say, from every pixel you have to compare its distance with all the boundary points, okay, and then find out the closest neighbors. All right, and this process you have to do for every pixel within this region. So there is a very high amount of such complexity which is involved in finding out the medial axis transformations, but lot of research efforts have been put into this, and a number of fast algorithms, okay, have been proposed in the recent past. All right, so I am not going into the details of the thinning algorithm or skeletonizing algorithm. If you are interested further, okay, you can refer to some of the references which I am giving you now, okay. Some references related to thinning algorithm or skeletonizing, because whenever you work with image processing, okay, many a times you will encounter situations where you have to do thinning or skeletonizing as a basic step prior to any object recognition or other high level image processing tasks. The references are, the first one is by Zhang Ty and Suen Cy, okay, Zhang Ty and Suen Cy. The title of the paper is A Fast Parallel Algorithm for Thinning Digital Patterns. The paper appeared in Communications of the ACM, Communications of the ACM, volume 27, number 3, page numbers 236 to 239, 1984. Okay, I repeat, Zhang Ty and Suen Cy. The title of the paper is A Fast Parallel Algorithm for Thinning Digital Patterns. It appeared in Communications of the ACM, volume 27, number 3, page 236 to 239, and it appeared in the year 1984. Okay, and subsequently some modifications were suggested in yet another paper, and the reference to that is this. Also you can refer. This is by Liu He and Wang PSP. The title of the paper is a comment on the above paper actually, a comment on a fast parallel algorithm, for thinning digital patterns. I am not writing it in full. For thinning digital patterns, that means to say it's the same paper. A comment on this particular paper, fast parallel algorithm for thinning digital patterns. And this paper appeared in Communications of ACM, volume 29, number 3, page numbers 239 to 242, and it appeared in the year 1986. Okay, this is the second reference which you can refer to. Although apart from these two references, there are a number of other references on the fast thinning algorithms. Okay, I'm not going into that. I mean, if you are interested, then you can scan for some of the latest literature which appear in the IEEE transactions on pattern analysis and machine intelligence, or in the computer vision, graphics and image processing, that is CVGIP, or pattern recognition letters. All these journals, okay, they will discuss. I mean, in every 2 or 3 issues you will find that some algorithms have been suggested for fast implementation of thinning algorithms. All right. So now this completes our discussion on the boundary representation. Okay, and now we are going over to the second problem, that is to say, after representation, okay, how to describe those boundaries. Okay, so now from representations we will go over to descriptors of boundary. A number of descriptors have been proposed, okay, and at first we will start with some very simple descriptors. Okay, so we start with some very simple descriptors, and in that one can consider some simple parameters like in order to describe a boundary, I think the simplest you can think of is to represent it by or describe it by the number of points which are there in a boundary pixel. Okay, rather you can describe it by the length. So the first simplest descriptor one can think of is by the length of the boundary. That means to say, you just count the number of pixels along the contour. Of course, by counting the number of pixels along the contour does not give you an idea of the total length, isn't it? Because the boundary will be something like this, and you are only counting that how many pixels are there in its boundary. But that is not one and the same as calling that this is the perimeter of the boundary, isn't it? I mean, we cannot describe it in terms of the length. No, it is not same as the length. I tell you why. Supposing we have a boundary like this. Supposing these are the boundary pixels. Now from here to here it is unit distance. From here to here, what is the distance? It is not unit distance, it is root 2 distance. Okay? Again unit distance, again root 2 distance. So if I take all the points like this, okay, and if I describe it by a length equal to n, I will be wrong, because the length of this contour is not equal to n. Rather, in order to describe the length, the length can be written as number of horizontal components in the chain code plus number of vertical components in the chain code and the third thing which we must have is root 2 multiplied by number of diagonal components in the chain code. So if we can have all these three numbers individually, number of horizontal components, number of vertical components and number of diagonals, or rather to say number of diagonal components and number of non-diagonal components, then we can calculate the length of the contour. Okay? And length is a very simple descriptor. Although length does not tell anything about the shape of the object, because I can have many number of objects, okay, which are having same length but which are having entirely different shape. Yet another simple descriptor, of course this is also not describing the shape, okay, but yet another simple descriptor which is often used in association with the length, okay, is the diameter. And the definition of the diameter is that diameter for a boundary B is the boundary, that's why I am writing it within bracket B. This is given by maximum of a distance function d. D is a distance measure between what? Between 2 points Pi and Pj, okay, where both Pi and Pj are points along the boundary, are points on the boundary. Okay, and the diameter B is going to be the maximum of these distances. All right, it's a very simple definition. I think it automatically follows from the usual definition we have for diameters. All right, and the third descriptor, third simple descriptor which we very often use is the curvature. Actually speaking, in digital image, it is very difficult to represent a curvature, okay, because there are all type of variations within a contour, and to represent a curvature digitally is really a difficult task. Okay. Now, one can of course represent the curvature by doing some simplifications, okay, like wherever we have, say for example, if we are having a contour like this, supposing we have a contour like this, now there at least we can have a measure of curvature at some of the prominent points of inflection, like say here. How we can do that is very simple. What we can have is, we can have polygonal approximation for this curve, okay, so that we get a polygon like this, okay, and then we take every linear segments, every straight line segments within this polygon, okay, and wherever we are finding that there is a change in the straight line, we can have a measure of curvature at this point by considering the difference of slopes of these two straight lines, okay. So, curvature at the point of intersection, okay, at the point of intersection is defined as the difference between the slopes of adjacent boundary segments. Difference between slopes of adjacent boundary segments. Now, we can say that a point P belongs to a convex segment, okay, if the change in slope is, I mean, if we are traveling in the clockwise direction, then we can say that a point P belongs to a convex segment if the change in slope is going to be non-negative, and otherwise we can say that it belongs to a concave segment. Okay. So, curvature is yet another descriptor. Now, these are all very simple descriptors, and as I told you that it doesn't speak much about the shape of the region, or rather the shape of the boundary is not specified clearly unless one takes a number of simple descriptors together. All right. So, there are other descriptors other than this set of simple descriptors, and the one which is very often used and one which is a very popular descriptor is by using the shape number. Okay. And let me tell you what the shape number is. So, simple descriptor was the descriptor number 1, and the number 2 descriptor is what is known as the shape number descriptor. In shape number, what we really take is the first difference of the smallest magnitude, first difference of the chain code. We take the first difference chain code for a particular boundary, and then we choose the starting point such that it gives us the minimum integer. All right, like the one which we described in the previous class. Okay, that you choose the starting point in the chain code in such a manner that it gives you, I mean, such that the resultant chain code sequence which you get, okay, that is the minimum integer. Okay. So, using this one can form the shape number descriptor, and shape number is actually given by the first difference of the smallest magnitude. So, shape number is the first difference chain code of smallest magnitude. Okay. And there is yet another parameter which is associated with the shape number, that is to say the order of the shape number. Now, the order n of a shape number is defined as the number of digits in its representation. Order defines the number of digits in the chain code, okay, and shape number is the first difference chain code of smallest magnitude. All right. Let us illustrate this with some example. Supposing I have got a region like this. Supposing, I mean, you consider these grids only and consider a region that is bounded by these 4 pixels. Okay, a very small region I have chosen. And what is the order of this particular region? What is the order for the shape number? So here the order is equal to 4, because there are 4 pixels. Okay, I mean 4 boundary pixels. So chain code will consist of 4 elements. Okay. Now let us have this as our tentative starting point. Supposing this is the starting point. Okay, and from this point we will be traveling in the clockwise direction, let us say. So what is going to be our chain code if we are considering a 4 direction chain code? Consider a 4 direction chain code. So this will be, I think, 0, 3, 2, 1. All right. Now tell me the first difference in the chain code. What is going to be the first difference of the chain code?
1.
From 0 to 3,
1.
we are going to have
1.
1. From 3 to 2, we are going to have 1, 1, 1. So, what is going to be the shape number? Shape number is going to be 1, 1, 1, 1, because even if you rotate 1, 1, 1, 1, okay, it is going to remain as 1, 1, 1, 1 always. So that is the integer of smallest magnitude. Okay. So here the shape number in this particular example, shape number is 1, 1, 1, 1. All right. Now consider some boundary like this. Okay. What is going to be the order of this? Order is going to be 6. Tell me the chain code.
0, 0, 3, 2, 2, 1.
0, 0, 3, 2, 2, 1. Alright. What is going to be first difference chain code?
0, 1.
Is
0, 1, 1, 0, 1.
0, 1, 1, 0, 1, 1. Okay. And in fact, in this particular case, even this is also going to be the smallest magnitude. Okay. So this is one and the same as the shape number. Shape number is equal to 0, 1, 1, 0, 1, 1. Okay. So like this we can consider several examples, and what we have to do really is first form the chain code. Okay. Take any starting point, form the chain code, and then form the first difference chain code so that you make it rotation invariant. Okay. And then you choose the starting point so that it gives you the minimum magnitude first difference chain code. Okay. And that is nothing but the shape number. Okay. So shape number is very often used as a boundary descriptor. Okay. And it really tells you much about the shape information of the boundary. Okay. It is a popular descriptor that is used. And yet another descriptor, okay, which has been very widely used is what is known as the Fourier descriptor. In Fourier descriptor, what we do is we consider a digital boundary. Okay. Consider an endpoint digital boundary. Supposing we have a digital boundary consisting of n number of pixels like this. All right. And we can consider these endpoints. I mean, all these endpoints are going to have an x coordinate and a y coordinate. Okay. So all these endpoints can be written as a pair of coordinates like x0, y0, x1, y1, x2, y2, etc. Up to x n minus 1, y n minus 1. Okay. And supposing these are the set of pixels which we obtain by traversing in any reference direction. Let us say we have got this set of points by traversing counterclockwise. Now why counterclockwise? Okay, you can ask me that why are we traversing counterclockwise over here? Okay, the reason is that in trigonometry we always take the angle as the traversal in the counterclockwise direction. I mean, basically this is our 0 degree axis, this is pi by 2, pi, 3 pi by 2 and 2 pi, and that's how we consider the angles in trigonometry. And because after all we are going to consider Fourier descriptors, okay, we have to represent in terms of the angular values will come in automatically, and we are considering the direction of traversal as the counterclockwise direction. And supposing these are the n number of points. Now instead of writing the points as x suffix 0, x suffix 1, okay, I can have an alternative representation, so that let us write x suffix k as x of k, okay, and y k as y suffix k, okay. I mean, basically we are not changing anything, we are only representing k as an argument of x, okay. Instead of writing k as a suffix, we are writing k as an argument, so that our points are now represented as a pair xk comma yk, okay, where k is equal to 0, 1, 2, etc., up to n minus 1. Now, instead of considering every point as a pair of coordinates like this, okay, I can have an alternative representation. I can imagine that my x-axis is the real axis and the y-axis is the imaginary axis. I consider a representation whereby I consider the x-axis as the real axis and the y-axis as the imaginary axis. If I have that representation, then every point which is now being described as a pair of coordinates can then be written in terms of a complex number, right? So each point can then be represented as a complex number s of k, where s of k is to be written as xk plus j of yk, alright, with k varying from 0, 1, etc., up to capital N minus 1. Please remember that by representing this way, I am not changing the nature of the boundary in any way, okay, but I have converted the problem from a two-dimensional one to a single-dimensional problem, okay. Basically, my points were having a pair of coordinates x and y, okay, and right now I am having only one point representation, and that's a complex point representation. By having a complex point representation, I am just reducing it to a complex one-dimensional sequence. So ultimately I am having a sequence S0 to Sn minus 1, one-dimensional sequence of complex numbers. So now, since I am given with a 1D sequence of complex numbers s of k, okay, I can take its Fourier transform, okay, and the Fourier transform, let us take the, let us say that the DFT of sk, okay, can be written as, let us put it as a, and I put the argument as u, where u stands for the frequency domain representation argument, okay. K was in the spatial domain, okay. K was the set of K is the index for the spatial domain of points, and u is the index for the frequency domain. So I am going to write it as AU equals 1 upon n summation k is equal to 0 to n minus 1 s of k exponential to the power minus j 2 pi uk divided by capital N, okay, where u is equal to 0, 1, 2, etc., up to n minus 1, okay. Now what is going to be the nature of this AUs? Real, imaginary, complex?
Complex.
In general, it is going to be complex. Okay. So all these AUs, okay, are nothing but the complex coefficients. All right, and AUs, okay, AUs are known as are called the Fourier descriptors of the boundary. AUs are known as the Fourier descriptors of boundary. Okay. Now, if I represent a boundary, okay, by a set of points, okay, I can transform it to a set of Fourier descriptors. And alternatively, if somebody gives me the Fourier descriptor, somebody supplies me with the Fourier descriptors values, okay, I can reconstruct the original boundary. All right. So to get the original boundary, what I have to do, if somebody gives me AU and I want to get S of k, what should I do? I have to take the inverse DFT. So inverse DFT expression is simple. Simply I have to write S of k as summation over U. What is the limit of U? 0 to n minus 1, because there are going to be capital N number of Fourier descriptors. And what is going to be the argument over here? AU exponential to the power plus, obviously plus, j 2 pi uk divided by n, and this we have to compute for k is equal to 0, 1, etc. up to capital N minus 1. Okay. Now, this is true if we have all the capital N number of coefficients, capital N number of Fourier descriptor coefficients. But usually it is found that all the capital N Fourier descriptor coefficients are not really necessary in order to have a reconstruction of the boundary. It is generally found that the first m coefficients, if we take only the first m coefficients out of the n values of AU, okay, where m is less than n, okay, if I take the first m coefficients, okay, of AU, then usually it is found that that can sufficiently represent the boundary. Okay. So in Fourier descriptor we need not consider all the n coefficients, we can have a reduced set of Fourier descriptors in order to reconstruct the boundary to a reasonably good extent. Alright. So if we do that, that means to say consider only the first m coefficients, we can write the sequence as S of k equals summation u is equal to 0 to capital M minus 1 AU exponential to the power j 2 pi UK divided by capital N, okay, where M is a number much less than N, okay, and this we have to do for k is equal to 0, 1, etc. up to n minus 1. So although we are given with m number of points for AU, okay, that is to say m number of Fourier descriptors, still we can reconstruct the capital N number of points in the spatial domain for the boundary. Now, like we have the usual representation of Fourier coefficients, okay, where the lower values of u's indicate lower frequency and higher values of u indicate higher frequency. Here the representation, or here the interpretation will be like this, that the lower frequency Fourier descriptors really give us an idea of the global shape. The lower values of u, okay, they define the global shape, whereas the higher values of u, they give the finer details. All right. So if we would like to have a global descriptor or a global descriptor of shape, what we should consider is only the first few Fourier descriptor coefficients. Okay, unless we are interested in very fine details, we need not consider the higher values of, higher use, okay, out of the Fourier descriptors. Any question?
Okay, thank you.